Hello and welcome to Chapter 8, Polyprotic Acids. In this video we are going to be dealing with phosphoric acid, H3PO4. And it's a polyprotic acid because it has more than one hydrogen, and it's going to release more than one hydrogen because of that. Now, that wording, it's a little bit funny, so let me show you what I mean visually. Let's start off with our usual first step. Identify major species. So we have our phosphoric acid, which is H3PO4, and we need to know if this is a strong or weak acid. And this guy you're going to want to memorize or learn to realize that it is a weak acid. We have the strong ones memorized, so if it's not part of our exclusive list, then we know it's not a strong one. Then we would write out the reaction. So this is where you're going to see what I mean by more than one reaction, or more than one hydrogen being released. So the first one we'll write out would be H3PO4, and it's weak, so what kind of arrow do we use? Double-sided arrow, and we'll have it release one hydrogen first. That is going to make phosphoric acid become H2PO4 with a negative charge. So notice how it used to be H3PO4, and now it's H2PO4 minus. That's one step. Now there's going to be another step. Take that H2PO4 minus. It'll be the beginning of your next reaction. Oops. Draw your double-sided arrow, and now we're going to release another hydrogen into the wild, but you're going to end up with HPO4 minus. And it still has a hydrogen to release, so it's going to happen again. HPO4 2 minus, double-sided arrow, another hydrogen, plus PO4 minus. And no, you cannot just write H3PO4 reacts to form 3H plus PO4 minus. The math won't work out if you do that. So we're going to do the same steps we usually do for a weak acid 3 times. We will write out an equilibrium expression for this first one. I'm going to label them here. This will have Ka1, and if you look up at the top, we've been given Ka1. It's up here. The next one will be Ka2, which is also given up at the top, and Ka3. So I'm going to have to do an ice chart, an equilibrium expression, and all of that good stuff for each of these, so 3 ice charts. In other words, this is going to be a long video. I'm sorry. So step 1, I need to write out my first equilibrium expression. So this is Ka1, which is equal to, so I need my products over my reactant. I have H plus H2PO4 4 minus, and my reactant is H3PO4. And I know my Ka for phosphoric acid, it's up here at the top. There it is, I'm underlining it. So this is equal to 7.5 times 10 to the negative third. All right, so now that I have my equilibrium expression, I want to actually get concentrations that I can plug into there. Make sure there's nothing being diluted. I don't see any dilutions, so that means I go straight to an ice chart. Set up first ice chart. So let's see, ICE H3PO4 H plus H2PO4 minus. Okay, so I know my starting concentration, I think. Let's look for it. Aha, here it is. I know my starting concentration of phosphoric acid. It's 0.500. And I know at the very beginning, when this whole thing started, I don't have any reactants. So at this point, you could try to finish this ice chart without me, and then come back to see if you got it right. If you're sticking around, let's see, do I need an X? Well, I don't know any equilibrium concentrations because this is a weak acid, so I'll assume this is negative X, positive X, positive X, because I'm losing reactants and gaining products. So 0.500 minus X, X, X. Now, we'll move on to step 5, which is plug into the first equilibrium expression. So I know, let's see, it'll be x squared, because I have x times x, over 0.500, that's a decimal, minus x is equal to Ka1, which I know is given as 7.5 times 10 to the negative 3. Okay, so right now you could assume that x is small and solve for x that way. However, spoiler alert, it's going to fail the 5% rule test. It will fail it. So I'll put that note on here. If you were to do the small x assumption, it fails the 5% rule. So in order to make this video shorter, I'm just going to spoil that for you and go on. So since it fails the 5% test, that means we need to use the quadratic. So I'll put that on here too. Use quadratic. Okay, so let's see, if I were to rearrange this, I would end up with x squared plus 7.5 times 10 to the negative third x plus 0.00375. Just a heads up, I need to sneeze. I hope I don't sneeze in your ear. All right, so we know that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, moving down more. Whoop, there. So let's plug in, let's see, x is equal to negative 7.5 times 10 to the negative third. And again, this is something you could try without me. You could like mute the video and then check it at the end. B squared, so that's still 7.5 minus 4 times A times C all over 2A. So if you were to plug this in your calculator, you'd end up with, according to what I have here, plus or minus point, let's see, well, let's back up a little bit. You'll get a positive number and a negative number. However, we're going to choose the positive one because concentrations can't be negative. So we'll end up with plus 0.0576. Choose the positive one because concentrations cannot be negative. So now I'm going to use this to figure out concentrations from up above. Let's see. I want to know the concentration of my H3PO4 as one of my answers. So here's my exciting answer color. The concentration of H3PO4 is equal to 0.500 minus 0.0576. You'll end up with 442 molarity. We will also find the H2PO4 minus. Oh, I shouldn't move it down quite yet. So looking up at our ice chart, H2PO4 minus is simply X. I'll box that. That's an answer. Now my hydrogen concentration is important. Let's get that. It is also 0.0576 molarity. I'm not going to box it yet though. Why would I not want to use that hydrogen ion concentration yet? The answer to that question is we have more hydrogens that are going to be released in these other reactions. So I can't erase it yet. I'm still going to use it. All right, I hope I'm going to have enough room here. Let's just go for it. So now we're going to repeat the process. 6. Write out the second equilibrium expression. So this will be our Ka2 is equal to, so we're going to use the second equation from the top of the paper. You should be writing this down so you can look at yours. It'll be H plus, this time it becomes HPO4 minus over H2PO4 minus, oops, that one up there is minus 2. There. All right, and we know what this number is. It was given at the top, so this will be 6.23 times 10 to the negative 8. So now that I've written this expression, what's next? Ice chart. So before you go off and do this on your own, make sure you get the correct initial concentrations. I know I have, what is it, H2PO4 minus, H plus, and HPO4 2 minus. So my starting concentration of H2PO4 minus is the same as the one I have written up above this. So I'll have 0.0576. Now usually we say, oh well, there aren't any products at the beginning. But here's the thing. Our last reaction created some hydrogen. So I need to include it. That gets thrown in the mix. And HPO4, that, however, has truly not been created yet. So that's not in my ice chart. So again, I don't know any equilibrium numbers, so I'll assume X, and I'll end up with 0.0576 minus X, 0.0576 plus X, and X. Great. Okay. I'll see if I can get this down here. No, it's just not going to fit. Okay, so I'm moving back up. Take a good look at what's on here. Write it down if you need to. And it's gone. So step 8 is to plug these x's, plug into your second equilibrium expression, and we want to solve for x. Okay, so I know that my, let's see, I have x times 0.0576 plus x over 0.0576 minus x is equal to my Ka2, which is given up at the top. Here it is, 6.23 times 10 to the negative 8. All right, let's try assuming x is small. Assume x is small. So if I were to do that, then I would be able to get rid of the x's that are being added and subtracted. And I'll end up with something much, much easier to solve. For 0.0576. So doing that, you'll be able to find x is equal to 6.23 times 10 to the negative 8. That's a small number. That's good news. Let's check the 5% rule. I'm going to do that on the side. Again, you should not do this on the side on yours. Make them nice and neat. I just am working with very limited space. So check my 5% rule. 6.23 times 10 to the negative 8 divided by what it's being compared to, 0.0576 times 100, is equal to, actually, I need to find out. One moment, please. 6.23 times 10 to the negative 8th. Okay, you end up with 1.08 times 10 to the negative 4, which is less than or equal to 5%, so we're good to go. We did not have to use the quadratic on this one. Okay, so once I have that, then I can start using my x to figure out different concentrations. So let's just take a look back at our old ice chart, just to refresh ourselves. I know x is equal to HPO4 2 minus. I know it's 0.0576 plus x is my hydrogen, and 0.0576 minus x is my H2PO4 minus. So let's do that. H2PO4, what is this, minus, oh, yeah, is equal to 0.0576 minus x, which was 6.23 times 10 to the negative 8, which is equal to 0.0576 molarity. Awesome. So that's good. I'm going to stop boxing things for now. We'll just box them at the end. HPO4 2 minus. That one was just straight up x, so 6.23 times 10 to the negative 8th molarity. And my hydrogen ions, of course, always important, is equal to 6.23 times 10 to the negative 8 plus 0.0576, which again is just 0.0576 because x was so small. Okay, now moving on. Again, I'll box important answers at the end, but I think it's a good idea to stop for now. So we're going to do this again a third time. So write out third equilibrium expression. So this will be Ka3 equals, I'm using this guy over here, H plus PO4 minus over H PO4 2 minus equals the number that they gave me up at the top, 2.2 times 10 to the negative 13. Once I write out this expression, I can start plugging into my ice chart. Okay, I have to scroll down a little. ICE HPO4 2 minus H plus PO4 minus. All right, so my initial concentrations, you need to look at the previous problem to get them. My HPO4 2 minus is in the previous problem. I'm putting a star next to it. Should be 6.23 times 10 to the negative 8. My hydrogen concentration is from above as well. It hasn't changed very much. Interesting. And my phosphate concentration, I haven't had any pure phosphate yet, so that's just 0. Okay, once again, assume my x's because I don't know any equilibrium concentrations. So I get 6.23 times 10 to the negative 8 minus x, 0.0576 plus x, and just x. So that was step 3, or actually step 10. I'm not sure where the number 3 came from. So 11, we're going to plug into, oops, I'm losing it. Plug into the third equilibrium expression. So now that I have all my x's, I can plug them in. X times 0.0576 plus x over 6.23 times 10 to the negative 8th minus x is equal to 2.2 times 10 to the negative 13. All right. Again, spoiler, you can assume x is small. This would not be a given on a test. You'd have to try it out for yourself and find out if it works. So if x is small, then that means we're comparing it to very large numbers. Those go away. And you can solve for x. I'm going to try to save some space here. So you'll end up with x is equal to 2.38 times 10 to the negative 19. Before we can do anything with this x value, we need to check the 5% rule. So let's see, how did I do that last time? I did it in black on the side. Okay. So check 5% rule. Again, you should put this all vertically on your copy. I'm just trying to save space. So my x, 2.38 times 10 to the negative 19 over the number it's being compared to. If I choose the smaller number, the much, much smaller one, that one is harder. It's more difficult to pass the test using that number. So I'll use that one. If it can pass this test, then it can pass any test. So if you plug that in, you end up with a tiny, tiny number. Oops. Oh no, go away. Okay, you end up with 3.8 times 10 to the negative 10, which is less than or equal to 5%. So again, we are good to go, as promised. I wouldn't lie to you. So now that we've done that, we can actually use that X to figure out some concentrations. So let's see, I can figure out my hydrogen ion concentration. Now, since this is the end of the line, it's the last one I'm doing, this concentration I get for hydrogen is my final hydrogen concentration. I can box this one. So my hydrogen ion concentration is 0.0576 molarity. It didn't change much. Oh well. Okay, what about our phosphate? Phosphate 3 minus. Oops, this needed a 3 here. Uh-oh, how far back did I get that wrong? This needs a 3. If you've been screaming that in your head this whole time, kudos to you. You got it right. Okay, so PO4 3 minus is 2.38 times 10 to the negative 19th. It was just the same as X. Now this is the first time it's showed up, and it's the last time it shows up, so this will get boxed. Excellent, that's done. What about HPO4? Let's do that one. That one ended with the concentration of, oh dear, all right. Mm-hmm. 6.23 times 10 to the negative 8 molarity. So this is our final HPO4 2 minus, so I can box it. Now I'm going to go back through my work and find the final times that everything else showed up and box those. So going back a step, hydrogen showed up later. I'm not going to box it. HPO4 2 minus showed up later. I'm not going to box it. H2PO4 minus, that, if you scroll down, does not show up in our last step. So since this was the last time it showed up, this one gets boxed. That's the last time we used it. Now let's back up to the very beginning. The first time we did this, I boxed some stuff I should not have. Let's see, my H plus showed up again. I couldn't box that. My H2PO4 minus, it showed up. We just boxed it right up here. So let's see if I can finagle an eraser here. Oh, this is going to take forever. Haha. Oh, that's too big. So that should not be boxed because it shows up again later. Now our H3PO4 minus, or H3PO4, no charge at all, that one, it only showed up in the very first equation. So it was okay to box that because it doesn't show up again later. So those are all the concentrations that we can find using ice charts. However, this problem also asks us to find the concentration of the OH ions as well as pH and POH. So we comply. Solve for pH, POH, and concentration of hydroxide ions, and then we're done. You could try doing this without me. That'd be a good idea. pH is equal to the negative log of the concentration of the hydrogen ions. So again, I'm saving space, so I'm writing across the line. You should not do that. pH is equal to 12. Now, how many sig figs do we want? 1, 2, 3. 3 sig figs inside of this log. So it went through the log, so that means that my answers sig figs only count after the decimal. So 3 sig figs is like that. 12.760. Okay, that's my pH. So I can find my POH by saying, well, pH plus pOH is equal to 14. So pOH is equal to 14 minus 12.760. So pOH is equal to, oh, dang it. You know what? This is the problem with me doing the work ahead of time and reading it. I scramble things, so I apologize. pH. I can hear you making fun of me now. Let's try that again. Your pH comes out to 1.240. My apologies, chemistry students. There. Okay. So we'd have 14 minus 1.240, which would give you a pOH of 12.760. That's where I got the number from. Okay, that's good. Now I need to figure out the concentration of hydroxide ions, and there's more than one way you can do it. Personally, I don't like working with logs, so I'm going to use this handy-dandy little trick. The hydrogen ion concentration times the hydrogen ion concentration is always equal to 1.0 times 10 to the negative 14th. So that means that my, running out of room, I'll divide both sides by hydrogen concentration. My OH concentration is going to be 1.0 times 10 to the negative 14th divided by my hydrogen concentration, which was 0.0576, which should give you, let's see, 1.74 times 10 to the negative 13. And it's a concentration, so stick a molarity symbol on there and be done with it. All right, so this is a polyprotic acid. I'm sure you're really excited to do a problem like this on a test. So just to go over what happened. We saw that H3PO4 has more than one hydrogen. We wrote an equation that shows it losing one hydrogen. Then we took that new product and showed it losing another hydrogen. Then we took that new product and showed it releasing another hydrogen. We wrote an equilibrium expression for each step of the reaction. We started at the beginning and we moved our way down. Each time we went through the reaction, we had a new hydrogen ion concentration to use in our starting hydrogen ion concentration in our new ICE chart. Then we solved that ICE chart and we eventually had final concentrations, solved for pH and pOH, and we were done. I hope that made sense. If not, go ahead and watch the video again. I hope you have a great day. Wait, no, I don't hope you have a great day yet. We need to figure out, oh, it doesn't ask if it's acidic or basic. Well, let's figure it out anyway, and then I'll wish you a happy day. What do you think, acidic or basic? It's got a low pH, very low. It is acidic. All right, now you can go. Have a good day.